Hello everyone. In this video we are going to look at beam bending and flexure formula. As always, my material are mostly taken from Mechanics of Material by Jure and Brooks. So here we are going to look at beams and the difference. You might say, what difference do you see here between this one and a bar that you're applying axial loading? That's exactly the difference. In bars, we typically apply axial loading. In beams, we apply lateral or basically transverse loading. So they bend. They don't just change their size, get longer or shorter. They bend. And this is what we are after. We want to see how they bend, what is the shape they're going to get, and how much stress will be created inside them as a result of that. So when they bend, they get the shape of a curve, which we call it deflection curve. And this vertical displacement that they have from their equilibrium position, this V, is what we call deflection. Okay, so deflection is this vertical displacement, this deformation, not displacement, deformation actually. Now, of course, since they get the shape of a curve, any curve, as you know, has something called curvature. So what is curvature? Curvature for any curve can be defined as locally, because this is a local thing. But if you have pure bending, and we're going to talk about that, in pure bending, this rho and k could be one single number for the entire beam. But if the m is variable and it's not pure bending, then you cannot define it as a single number. But first of all, so since I mentioned it, and I mentioned it already down here, what is pure bending, which is what we're going to see here? In pure bending, we assume that the bending is uniform all across the beam. So anywhere you cut on that cross section, you only have a single M value, and that only happens when there is no shear force, there is no transverse force on the beam. Okay, so here, that is what I mentioned for you over there. So we first study that, and then we look at more general cases where M could be a function of location. But right now, if we assume that this bending moment M is constant, then we can define a single radius of curvature rho, and the reciprocal of that is what we call the curvature. Okay, so you see the unit of curvature is 1 over length, and rho is the radius of curvature. So if you consider this curve, you can say that there is a point that is called center of curvature, and there is a radius of curvature. Okay, now again, this radius of curvature is either something local, a function of x, or it could be something global, depending on how the bending moment M is changing. Whether it's constant, we call pure bending, or non-uniform bending. But even if we look at it locally, so basically what this radius is the radius of a tangent circle. So if at any point you can draw a tangent circle to the curve, the radius of that is called radius of curvature, and the center of that is called center of curvature. Good? Now, and we show it with parameter rho. Now here, if we consider 2 points that are very, very close on this curve, on this deflection curve, M1 and M2, so that the distance between them on the curve is ds, and the horizontal distance between them is dx, and the angle between these two radial lines connecting the center of curvature to M1 and M2 is shown by angle d theta. Clearly, from the definition of d theta, we can find that d theta is what? Well, d theta is in radians. You know, any angle in radians, the definition of that is the length of the arc in front of it, which is ds, divided by the radius of the arc, which is rho. So d theta is ds over rho. If you swap these two, you can see that rho equals ds over d theta. So this is the value of radius of curvature, ds over d theta. Now, of course, it's not easy to find ds over d theta, because you have to find s as a function of theta. And most of the time, s, you can find it as a function of x, not as a function of theta. So finding the radius of curvature from this formula is not something easy you can do, but that could be a starting point. Now, k, which is 1 over rho, is of course d theta over ds. Okay? Now, for typical beams in structures, the curvature and the deflections are very small. So these V values that I just showed you, they are very small, okay? These numbers are very small numbers, and the curvature is very minimal, or the radius of curvature is very, very large. In that case, okay, when this rho is a very big number or k is a small number, we can say that your ds is approximated by dx. Why? Because if you remember, this ds is kind of like basically, if you consider it like a right triangle, so this ds is like the hypotenuse, and dx is this bottom side here, and this is dv or dy, okay, and this is that angle d theta. And when this number is very small, you can see that ds, which is the square root of dx squared plus dv squared, clearly is going to be the same as dx when the deflection is very small. So I can replace the ds in both of these with dx. If that's the case, then I can say that d theta over dx, which is the change in the angle of deflection, theta over the location, that is k. By the way, this k can be positive or negative. If it's curving upward like that, k or curvature is positive. If it's curving down like this, curvature is what? Negative. And this is basically the same as the second derivative that you had in calculus. So, going forward, now we want to look at the strain and the stress in any location along the beam as a result of this bending. So here we make an assumption and we say that the beam was basically initially a straight longitudinal axis. So initially beam was straight like this, it wasn't bent. And then the cross section of the beam, so this is just a 2D view of the beam, but if you look in 3D, this beam has a cross section, correct? This cross section here is symmetric about the vertical axis. So if you look at the cross section here from the side view, if you look at this view, this is the y-axis that is passing through the middle of this cross section, and the cross section is symmetric about the y. Okay, so half of the cross section is in front of the xy plane, the other half is behind it. If that's the case, we can assume that when the beam is bending, if you consider all of these different lines that were parallel on the longitudinal direction when beam was not bent, when they are bent, they're gonna be all basically curves with the same center here shown by this point, and with the same with different radii but with the same center, and the angles that these curves are making with the radial lines, so these are those radial lines and these are the curves, the angle that are made are still at 90 degrees. Remember, originally the vertical lines and these horizontal longitudinal lines were at 90 degrees. Even after bending, they are still staying at 90 degrees, which again mean that these are all parts of a circle. These lines all become part of a circle, all centered at the same point. So those radii are perpendicular to the curves. Okay, so in other words, if you look at these different elements, they don't distort and they stay normal to these what we call these longitudinal lines. And there is one of them that we care about the most, as we'll see in a second. That is the one that is passing through the centroid of this cross section here, and that is what we call the neutral axis. So all of these individual elements, they are all going to stay perpendicular to the neutral axis. That is going to make my geometry calculations a lot simpler. Now, moving on, let's see how we can calculate this now. So here is a small element inside the beam that is bent. So this beam goes from left to right. And here we are only focusing on a small component of it. with the length dx, and we are not only focusing on that dx, we are also focusing on this arc here, EF, which is not exactly in the middle. It's at a height of y above this mid position. Okay, and you might say, what is this mid position? What is this arc SS? I'm going to show you. Okay, that's what we call the neutral axis, and I'm going to explain what that one is. But this here, this arc that I'm going to focus on is at the height of y above this neutral axis. I'm going to focus on the formation of this arc. So before I move on, I need to clarify the notion of neutral axis because I mentioned it several times. What is neutral axis? Well, let's go back and look at this picture again. So remember, initially, as I said, the beam was horizontal like this. And if I consider a bunch of lines along the beam, some longitudinal lines like this, look at them before and after the bending. What would you see? Well, let me use different colors here. So you'll see that there are some of the lines, like this black one, that after the bending is occurred, you can see these lines get shrunken, get smaller. They are under compression. There are some other lines at the bottom that you'll see if you track them after the bending, you're going to see they got longer. So you see there are some areas at the bottom that are under tension and they get longer. There are some areas on the top, in this case, that they are under compression and they get smaller or shorter. So from this region of tension or positive sigma to this region of compression or negative sigma, you have to pass through a region that has 0 sigma because you're going from negative to positive or positive to negative. There should be a 0 crossing somewhere in between. And that is exactly the location we call the neutral axis. So there is a line here that if you followed it, the length of this line, although it's bent, but that's the same as what it was before bending. So only for this region here, there is no stress and no elongation or compression or nothing. That axis is what we call neutral axis in 2D, and in 3D, if you look at it, if you draw this guy in 3D, of course, that corresponds to a surface, correct? That blue curve in 3D, if you look at it, that corresponds to a surface like this. And that is what we call neutral face or surface, not face. Okay, so the neutral axis, you can see it along the beam, and you can see it if you follow it, because it's a part of a surface, you can see it on the cross section. So on the cross section, you're going to also see the neutral axis. And we typically show the neutral axis with dashed dotted lines. So if you see dashed dotted line anywhere, that is basically your neutral axis. Okay, so this is your neutral axis here. And in this one, again, you better use dashed dotted. So if you see something like this, that is the region that has no stress or no strain. That is the neutral axis. Okay? Now, where is this neutral axis? Is it always in the middle? No. It depends on the cross section. Where is it on the cross section? I'm going to show you in a second. If you look at the cross section, the neutral axis always passes through the centroid. So if you find the centroid of the cross section, that is exactly where the neutral axis is passing. And I'm going to show you in a second. But we know where it is. So now when I come down and look at this second picture, this height y is measured from the neutral axis. So this SS dash line or dash dotted line in general, that is your neutral axis. So now we're going to look at the deformation of this element EF. Initially, it was only a line with length dx. Now it is a curve with angle d theta in front of it. And what radius? So what is the radius from this EF to the center? What is this radius from here to here? Well, rho, the radius of curvature that I introduced initially, that is from center to which line? That is from center to the neutral axis. Okay, so the parameter rho is measured from the center to the neutral axis. Now your y units above the neutral axis, so the distance, radial distance from this EF to the center is rho minus y. Good? Okay. So now, let's look at this part. If I ask you, what's the length of this arc from E to F? If I call it L1, the length of the arc from E to F, what would you say? Well, in this figure, you say, well, I have these two lines. Both of them are rho minus y. The angle in front of it is d theta. And this is this arc with length L1, that's EF. So L1 is clearly rho minus 1 times d theta. Now, what is d theta? I want here to go back and look at what I derived earlier. Look at here. I want to relate it to rho. Remember I said dx and ds are the same thing for small deflections. So if I look at this relation here, let's look at this. If I replace ds with dx, you can see that d theta over dx is 1 over rho. So if I want d theta, what is d theta? D theta is going to be dx over rho, correct? From here, you can see cross multiply. D theta is dx over rho. So if I go down here, that is what you can see. That d theta is replaced by dx over rho. And so here I multiply, so it's going to be rho times dx over rho. These two rows would cancel, you get the dx. And then here you get negative y over rho dx. So this is the length of the element. Yes? This is the length of the element after deformation. Now, what is the length of the element EF before the deformation? Well, it was simply dx. So the current length is this. The initial length is this. So if I want the normal strain, remember normal strain epsilon was what? It was delta L over initial L. So delta L is L final minus L initial divided by L initial. And if I plug in this L1 here, okay, those two dx's would cancel. And then this dx with this dx would cancel. And clearly you get negative y over rho. And 1 over rho is k, so you can also write it as negative k over y. So here we go. We found a formula for the normal strain. Normal strain is negative y over what? Over rho. This is the strain at location y above the neutral axis. So if you are at the neutral axis, how much strain would you get? Of course, 0. Is that correct? Yes, because there is no stress here and there is no strain here. Now, if you go above the neutral axis, so your y is positive, you are above the neutral axis in this case. Clearly, because rho is always a positive number, your epsilon is going to be negative. And negative epsilon means what? Means negative stress. Negative stress means compression. Is that the case? Yes. Look here. You see above the neutral axis, you have sigma negative and epsilon negative. Below the neutral axis, you have positive sigma and positive epsilon y, because here y is positive. And up here, y is negative down here. And up there, y is positive. And remember, epsilon was negative y over rho. So the sign of strain and the sign of y are opposite of each other, as you can exactly see here. And it does make sense. And of course, since I said the rho is typically a very large number for beams, and this y can at best be from what to what? If you look at the cross section, and let's say the height of this cross section is h, correct? And this is a rectangular cross section for a moment, and the centroid is in the middle, the y can at most be plus h over 2 and what? Negative h over 2. That's all it can change. But rho is a big number. So rho could be in tens of meters or hundreds of meters, but this h is typically much smaller. So when you divide, you expect very small numbers for the strain, which is exactly what we expect to have. Small numbers for the strain. Okay, now that I found my strain, all I need is to multiply it by Young modulus to get the stress, assuming that my material behaves in the linear elastic region. So sigma is E times epsilon. Epsilon was negative y over rho, so sigma becomes negative EY over rho, or negative EKY. So there we go. I found my stress at any location, which again, you see it has the opposite sign with y. And this is the stress distribution, as you can see. So if this point is the centroid, where the neutral axis z is passing through, you see below it at negative y's, sigma is positive. You see it's outside, it's tensile, and it's linearly increasing. At neutral axis, it's 0, linearly increasing to the bottom surface of the beam. And above the neutral axis, where y's are positive, all of the sigmas are negative, again linearly increasing from neutral axis to the top surface of the beam. So clearly the minimum stress is at neutral axis. The maximums are at the very top of the beam and the bottom of the beam. One of them is compression, one of them is tension. So this is sigma tension maximum. This up here is sigma compression maximum, and none of those numbers should surpass the allowable sigma. Otherwise, your beam is going to fail. Good. So here is the distribution of sigma and epsilon. Now, two things. One, I just mentioned a few minutes ago that the neutral axis is passing through the centroid. Well, how do you know? Here is the proof for that. Look, if I look at this beam here, and I say this beam is subjected to pure bending, so all I can apply to it in this case is bending moment, no axial force or anything. Okay, so the beam is not exposed to any axial loading. There is no load here, there is no load there at any cross section. Even if you cut, there is no axial loading anywhere. Then, since these sigmas are in the x direction, if I multiply these sigmas by small area, infinitesimal area dA, and sweep the entire surface with it, that should be all of the force that I will get in the x direction, because the sigmas are in the x direction, so I can get force in the x direction. But remember, I said there is no axial force, there is no x force. So integral of sigma dA should be 0. But what was sigma? Let's just replace it with what we had, negative EKY. So negative integral of EKY dA equals 0. Now E is a constant, you can simplify both sides with it. In pure bending, K is also a constant, so you can get rid of that. And look here, since this negative can be cancelled, you see that the integral of y dA is 0. What does integral of y dA 0 mean? About which point the first moment of area of a surface is 0? The only place that can have first moment equal 0 is the neutral axis. So you see that the location of the neutral axis is the location of the centroid. And this is assuming you have pure bending, because it's in pure bending that this K parameter is a constant value, and you can simplify it from both sides. Otherwise, this K is not going to be constant. This K is going to be a function of X. And that makes it a little bit harder. But here, we assume that we can put it through the centroid. And I mentioned that for you here. So this is correct when the material follows the Hooke's law. So sigma is E times epsilon, and there is, of course, no axial force on the cross section. Good. Now, with all that in mind, the next big thing we have to discover is what relation exists between this sigma and this bending moment, M. Right? So far, everything was assuming that I know rho or I know K. Well, guess what? I don't. I have no formula for rho or K. Okay? Everything should come from the loading, which is M. So if I make this bending moment bigger, I'm gonna have what? If I make M bigger, instead of a mild curve, I'm gonna have a much more aggressive curve, which means rho is gonna go down. So if M gonna go up, rho should go down, right? What's the relation between them? We're gonna find it. But here we have to find a formula for rho based on the moment, based on the bending moment. So how do we do it? We say, well, look at the cross section. If you look at any element here, dA, which is at height y from the neutral axis, if I multiply, and this is the cross section from the side view, and then here is the beam at that cross section. So that face is right there, and that element dA is right here, and sigma x is in this direction. So if I want to find the moment here about the neutral axis, which is right there at the center or at the centroid, how can I find it? Well, this is sigma x. If I multiply it by dA, that is going to give me the small force on that element, dF. And this distance, remember, this is y. So if I multiply that dF by y, that is going to be the small moment from that element. And if I integrate all of this, that is going to be the total moment. So I can say M is the integral of y dF, and dF is sigma dA, and that is exactly what you can see here. This is y. This is that dF force. And here I can add the constant force, or say this is equal to M. So or say this total moment is equal to 0 because the system is static. So the total moment is the bending moment at any point plus the distribution of the stress which causes another moment. Sum of it is equal to 0, or say M is equal that, as I said here. And now what? Sigma x, remember sigma x was K-E-Y. Remember that? K-E-Y with a negative sign. That was sigma. Look at it here. Sigma x is negative K-E-Y, or negative K-E-Y over rho. That is sigma here in this formula. dA is just directly replaced. And this y here is multiplied by sigma. Sigma already had a y. This is another y. That's why you get the y squared term. What happened to the negative? Well, this negative and that negative canceled. So M is going to be integral of K-E-Y squared dA. Now K and E, again, assuming they are constant, bring them out of the integral. So it becomes K-E integral of y squared dA. And what is this integral here? That looks to me like a second moment, right? Second moment for which axis? For this axis with respect to this neutral axis, because y is the distance to the neutral axis. So this one is I is the second moment. And if we call this neutral axis z-axis, right? Because x is along the beam, y is upward, z is in the cross section, I can call this IZZ. Okay, again, look back at the beam. This axis here is y, this axis is x, so z here is in the board, which is going to pass through the cross section. So that is IZZ. There we go. So I found the formula for M. M equals KE Y. So from here, now I can find my curvature K. K is M over E I. There we go. And K is 1 over rho. So now I found my rho as a function of M. And if you look here, you clearly see that M is in the numerator, rho is in the denominator. So if I make M go up, that means rho has to go down, assuming these other ones are constant. Okay, so you clearly can see the relation here. Now epsilon, the strain was what? It was negative K over Y, so I replace K, so the strain is going to be negative My over EI. And stress was E times that, so if you multiply this by E, that E and this E would cancel. The normal stress is going to be negative My over I. Again, what I? I of Z, Z, I about the neutral axis of the cross section. And this formula, this last formula, is the most important formula in this lecture. The normal stress at location Y with the moment M and the neutral axis to be the z-axis is negative My over IZZ. That is called the Flexure formula. That is the most important formula which shows stress inside a beam under pure bending. Okay, that is the most important thing. Good. Now, since I have the Flexure formula, I can go ahead and find my maximum tensile and maximum compressive stress, these two. Why those two? Because these are the maximum stress. You have to always compare them with the allowable stress in tension and compression to make sure the part is not failing. So the max compression and max tension stresses are very important. We have to calculate them. How? Well, all we need, if you look at this formula, negative My over I, assuming that again M is constant and IZZ for a cross section is constant, they are only function of Y, height. So when sigma is like this, sigma max is going to be negative My max over IZZ. And since Y max could go both ways in magnitude, then this is like plus minus, like this. So at maximum positive Y value, we're going to have maximum compression. At maximum negative Y value, we're going to get the maximum tension. So C1 and C2 here are the maximum height from the neutral axis. So if you have some arbitrary cross section like this, and this is the neutral axis, the maximum height from the neutral axis in the up direction, that is C1, and the maximum on the bottom side is what? C2. Okay? Now, if you look at these two, you see that if I bring this C to the denominator, I can write it as negative M over I over C1, and this way I can write it as M over I over C2. You see in both of them that I over C is an important parameter, the one that is in the denominator. So M over that I over C is the maximum stress. So that's where they gave this I over C a name, because it's only a function of geometry, the cross section, and they call it the section moduli. So the section moduli, I over C1 and I over C2, these are called the section moduli. Each one of them is a section modulus, S1 and S2. And so M over S, the section modulus, this is your sigma max. Now, if it's 1, it's going to be compression max. If it's 2, it's going to be tension max. Okay, so you're going to see the Flexure formula, the maximum of it is also written like that. Now, for well-known cross sections like rectangle and circle, we can easily find this section modulus. What is it? Well, if the cross section is a rectangle with width of B and H, height of H, clearly I about this ZZ axis is BH cubed over 12. and your maximum or minimum y is h over 2 plus minus h over 2. Since they are the same thing, both c1 and c2, then I over c is going to be this one over h over 2. So you simplify 1h this, and you get bh squared over 6. So that is the section modulus for this. For circle, I about the z-axis is pi d to the 4 over 64. D is the diameter. And maximum y or minimum y is d over 2. So you divide that by d over 2. Again, that 2 and 64 get the 32. D to the 4d get you d cubed. So pi d cubed over 32 is the section modulus for the circle. So if you divide m by these guys, those are going to give you the maximum and the maximum compression or tension in magnitude. Good? Now with all that, to practice what we learned in this lecture, let's look at an interesting example. So here we have a beam that is simply supported, pin at A, roller at B. There is a uniform load with intensity Q2 of 3 kilonewton on it. It has an overhang from B to C of 1.5 meter, and the span of the beam is 3 meters from A to B. Okay? The cross section of the beam is a channel with width of 300 mil, height of 80 mil, and the thickness of 12 mil. So what does channel mean? It's also called the C cross section, or U some people call it. So if you look at it, it's like this, and this is the B, this is the H, and the thickness anywhere is 12 mil. So the cross section is not a simple rectangle or not a simple circle for which we have the S. We have to find the I, ZZ, and the Y max or Y min in this case. We have to find these guys for this cross section. And for that, we need to use the stuff we learned in the statics about centroid and about the moment. So this is a good practice on that as well. Now you can see applications of centroids and the moments that you learn in statics. You're going to use it here right in solid mechanics. Okay? Now, here we want to find what? First, we want to find the maximum tensile and compressive stress in the beam due to this load. Second, if Q is unknown, so instead of being given, if we don't know how much it is, but we know the allowable stress in tension and compression for the beam are 110 and 92 megapascals respectively, we want to find how much would be that uniform load that you can put on the beam before it breaks. Now, one thing I have to mention here is this is clearly not a uniform bending. Why not? Because there is shear force. And as we learned, when there is shear force, bending will change. Okay? Bending will change when there is shear force. So here we just basically doing some approximations. It's not perfect. And what we do, we only look at 2 points on the beam, and we only use the single M numbers in those locations and not treat the whole thing as uniform bending. So first thing first, remember your sigma is what? Your sigma is negative my over I, ZZ. Now this IZZ is constant for the cross section. What we need to find is first where the centroid is, and then put the z-axis there, and then find IZZ. That is clearly going to be a constant number. But M and Y are variable in this beam. Not only Y is variable, you can go from this point up and down. You can also see that M is not constant. M, if you plot the bending moment diagram versus location, M is not going to be uniform. If you look at it, M actually does change because the shear force is non-zero. So if I want sigma max, what should I do? My goal is to find the maximum stress in this beam. Not only I have to make Y to be max, guess what? My M also has to be max. So I have to find where along this beam you have the maximum bending moment, and then on that location on the beam with maximum M, I have to go to the top of the beam or the bottom of the beam to find the spot that has the maximum stress in it. Okay, so I have to maximize both of these. And to do that, we have to draw, of course, the bending moment diagram. How do I do that? I have a separate video on the same playlist, Solid Mechanics. It's called Shear Force and Bending Moment Diagrams. Please take a look at that video and you'll learn how to draw these two graphs, V versus X and M versus X. Okay, if you do that, you're going to get this graph. And both of them are quadratic because M is an integral of V. So if V is a line, M is going to be a parabola. And you'll find that there are two spots in this beam that have maximum moments, whether positive bending moment or negative. In the maximum positive one, it's placed somewhere between A and B at the distance of 1.125. The maximum bending moment is 2.025 kilonewton meter, and it is related to the parameter Q by this formula. And there is another spot that is right at B. There is a maximum bending moment of with magnitude of 3.6 in the negative direction kilonewton meter, and it is related to Q by this formula. Again, look at that video to see how I can plot M versus X for this specific loading. Good? Now, where should I go on the beam? I should look at this spot and I should look at this spot. These two spots have the maximum M, and we have to also look at their maximum and minimum Y. So at these locations, what I have to do is to go on the top of the beam and at the bottom of the beam. So basically, I should look at four spots. One is here, one is there, one is here, one is there. And find the maximum tension and compression in these four spots and then compare it against the allowables. And my neutral axis is, of course, passing through somewhere here. Where? We'll find it. But there are four critical spots that I have to check to see which one will determine the failure. So the first thing I need to do is to look at the centroid of this. And for centroid of that, if you just break it down into three rectangles, like this bottom picture, and neglect these fillets, so break it down into three rectangles like you can see, then you'll find the centroid, and I'm not going to do the calculations for that, but if you do that, well, clearly, since this guy has an axis of symmetry here, you know the centroid should be on the y-axis, but where? Here, you'll find the centroid of each one of them. So the centroid of this AD is here at 40, the centroid of this one is also at 40, the centroid of this 12 is at 6 up here. So you find each and every one of these y's of their centroids, multiply by the corresponding area, and that gives you the y bar for the entire cross section. So it is going to be A1 y bar 1 plus A2 y bar 2 plus A3 y bar 3 divided by A1 plus A2 plus 3. And A's are the cross sections of these guys. So A for this one is clearly 12 times 80. The same for this one. This is also 12 times 80. And for this A1, as you can see, it is basically 12 times this length, which is 300, correct? Minus 2 times 12. So 300 minus 24 is 276. That is A1. And the y bars are clearly y2 bar is 40, y3 bar is also 40, and y1 bar here is half of 12, which is 6. So plug in all those numbers and you can get the y for the centroid. Let me see what number I have. It is going to be 1848 mil. So clearly it's below 12. It's 6.48 below 12. So this distance from here to here, that guy is 648 mil. That is where the centroid of the entire cross section is, and so your z-axis is going to pass through that. Now that you know where your neutral axis is, you can find y mean and y max. What are they? So one of them is this y, the other one is this y. How much are they? Well, the whole thing is 80. This is 1648, so this is clearly 1648. And this one is 80 minus 1648. So these are your y max, or y mean you might call, depending on the sign. You have to look at both of these numbers. Good? The other thing you have to calculate is IZZ. I about the z-axis, what is that? So here I need to calculate IZZ. I have three sections, three rectangles. So if I find each one of them and add them together, that's all I need to have. The problem is none of these shapes, none of these individual rectangles, their centroid is at the same location as the total centroid. So the total centroid is here. These guys' centroids are at different heights than this one. So if I want to find any of them, I have to use parallel axis theorem, right? So for instance, for shape 1, which is this guy, what was the eye of a rectangle passing through its own centroid? It is b h cubed over 12. Now b for this guy is 276 times 12 cubed over 12. This is the bh cubed over 12. This is for its own centroid plus the area of it, A1, let's see if I can move, times some distance squared. What distance? The distance between centroid of this A1 and the actual centroid. Now this is 6, that is 18, so that is going to be 12.48 squared. So I use parallel axis theorem for IZZ1, and then for ZZ2 and 3, I have to do the same. Now, since they are the same shape, I can only calculate one of them and multiply it by 2 like this, because they are identical shapes with respect to the centroid. So if I calculate the whole IZZ using parallel axis theorem, I also have that number. The total IZZ is going to be 2.469 times 10 to the 6 millimeter to the 4. There we go. So I have IZZ now also calculated, and I have my Y min and max. Now that I have all these variables and all these numbers calculated, guess what? I can go ahead and calculate my maximum sigma. Again, remember I have 4 hot spots. I have all of these 4 points. So I have to calculate the values for them, and I can get 4 maximum stresses for basically tension and compression. Now, where is tension? Where is compression? Well, to determine that, you have to look at the sign of the bending moment. You see here in the main span of the beam, the moment is positive up to a point basically to the right side of my critical point, it's positive, and after that it goes negative. Okay, and positive bending moment means you're gonna bend like this, and negative means you're gonna bend like that. Okay, now if you bend like this downward, you know on the top you have compression, and on the bottom you have tension. And here is the exact opposite. On the top you have tension, on the bottom you have compression. Okay, so if you don't mind calling these points point 1, 2, 3, and 4, I have to find the maximum compression anywhere in the beam by comparing values of 1 and 4, and by comparing 2 and 3, I have to find the maximum tension anywhere in the beam, and those will determine the failure. So I go to point 1 and 4. So sigma compression in point 1 is equal to negative m at this point, which is this number here, and I convert it to Newton meters, times y at that point divided by IZZ. And IZZ, remember, we have the number for it. It is 2.469 times 10 to the 6. And it's mil to the 4, so I have to also multiply it by 10 to the negative 12 to convert it to the meter to the 4. And the maximum y, remember, we had 2y, and now that I'm looking back at it, seems like I made some mistake. I found it to be 1848, but somehow I wrote 1648 here, which is, I don't know why I did that, probably being tired. So this is 1848, and this is 80 minus 1848. Okay, not 16, that is 1848. And so for point 1 now, if I go back and look at point 1 is at the top, so y of it is positive, and it is how much it is above the centroid, which is 1848. So I'm gonna write it right here, 1848, but it is in mils, so pay attention, you convert it to meters. So that is sigma of C1. If I go with 0.4, again, negative of, now m at 0.4 is this negative 3600, so I'm gonna write it down here. And then there is y for 0.4. Now, if you'll see, 0.4 is at the bottom, and y of it is negative. Negative how much? Negative of this number, which is 6152, right? So it is going to be negative 6152, and it's in mils, so convert it to meters. Again, divided by the same ZZ. And you can see both of the numbers will be negative something, because here these two negatives would cancel each other. I can find that. Finally, I do the tension in points 2 and 3. For point 2, the bending moment is that 2025, correct? But it's at the bottom, so y of it is that negative number, this one. And ZZ is the exact same thing. So it is going to be positive something this time, because that negative and that negative would cancel. The last one is, the y of it is negative 3600. The m of it, the y of it is that 1842 positive. Right, because we're looking at point 3, and point 3 is on the top, which has that positive y divided by the same IZZ. Z. Again, it's going to be positive because these two negatives would cancel it. So here I calculated the numbers and I'm showing it to you so you can clearly see the maximum tension and compression. So clearly the maximum compression anywhere in the beam is negative 89.8 at 0.4. The maximum tension is at 0.2, 50.5. Okay, so 50.5. So points critical are 2 and 4. These 2 points at the bottom. These 2 points are the dangerous spots. Depending on the material, whether it's stronger in tension or compression or equal, one of these two will be the ultimate failure point that you can have. Okay? So you see how I have answered part A. Now for part B, you want to know if the maximum possible tension is 110 and the maximum possible compression is 92, how much is Q? Well, for that, I have to come back here and look at these critical points and say that this one is going to be 92 instead, and this one is going to be 110. But instead of me having these numbers, instead of having those numbers, I have to use the equivalent formula. For the negative 3600, I have to use negative QL squared over 8. And for this one, I have to use 9 over 128 QL squared. And L is the length of the beam in this case, okay? So L is basically what you have, which is 3, right? Or L is 3 actually. L is not all of it. L is only this portion. This portion is L. So when it says over L, by L, they are talking about this portion, not all of it. So L is 3. So L is given. This is 3. Those numbers are given. From each one of them, you can find one Q. Here you solve for the top one. Q1 is going to be 3.28 kilonewton per meter. Bottom one, 6.97 kilonewton per meter. And which one would you pick? Always the smallest one to make sure nothing is failing. So answer to part B is 3.8 kilonewton per meter is the uniform loading that you can have without breaking any portion of the beam and staying safe. Okay, hopefully this long example was useful to you. You saw the applications of statics, the applications of bending moment and shear force diagrams, which I did not really do. But if you want, this takes some time, so I didn't want to make the video very long to show you how these graphs are generated and how to get to these formulas and numbers. And finally, how to use the Flexure formula to find the safest load you can have. Thank you so much for your attention, and I'll see you in the next video.